Hello everyone. This video will cover notes from section 5.1 and 5.1 deals with functions. We're going to start with this first problem that asks us to suppose we have f of x and it's equal to negative x to the third power minus 5x plus 6. We want to find f of negative 2. Now, as we relate f of negative 2 to our supposition at the beginning, we see we have f and some number x in parentheses. What you want to pay attention here is the negative 2 is replacing x. Therefore, we will take our function, and everywhere we see the variable x, we're going to replace x with negative 2. So f of negative 2 would be equal to our minus. We carry down our minus sign. And then for x, we substitute negative 2, raise it to the third power. Minus 5, and then x again in parentheses, we substitute negative 2, plus 6 at the end. Now we're going to simplify. In parentheses, negative 2 to the third power is negative 8. We carry down the minus sign in front, carry down here. Now, behind that negative 2 to the third power, we have minus 5 times negative 2, and a negative number times a negative number. Negative 5 times negative 2 gives us positive 10. Carry down the plus 6 at the end, and now we're going to continue to simplify left to right. Negative, negative, so minus 8 gives us positive 8. Plus the 10 and plus the 6. Now we'll add these three digits together. 8 plus 10 plus 6 gives us our solution, which is 24. So f of negative 2 equals 24. In the second example, we're finding the value of a function g of 0, g of 3, and g of negative 2, but this time we aren't given an equation for that function, we're given the graph of the function. Now recall what this g of x means in terms of us relating g of x to a linear function, meaning if this equation were written as y equals mx plus b, for example. This is the linear equation in slope-intercept form, and this g of x is the same as y. Remember, f of x is the same as y, and the same applies if that variable changes from f to g or some other letter. In this case, we're using g of 0. So we're really asking for the value of y, g of 0. What is that y coordinate when we're given 0 as our x coordinate? For the second example, g of 3, what is the y coordinate when we're giving 3 as our x coordinate? And then the last one, what is the value of y when we're given negative 2 as the x coordinate? So we'll look at this graph. Remember, your y-axis is the vertical line that runs up and down, and the x-axis is your horizontal line that runs left to right. So when we look for g of 0, we're going to go on the y-axis. Well, we're going to go on the x-axis to 0, which will be here where our pencil is. And we want to know, what is the value of y? Where does this graph intersect that line when y or x is 0? Where is the graph of the line? The graph is up here touching the line right here at 3. It's a little bit above 2 and in between 2 and 4. So it's right here at 3. When x is 0, the graph touches the line, the y coordinate is 3. So the value of that function, g of 0, is going to be 3. Now g of 3, now we're on the x-axis. We're going to go to 1, 2, 3 right here. Notice what happens with our graph this time. The graph crosses that line, crosses the x-axis. That's at point 0. So the y coordinate when x is 3 is 0. That graph touches the line at 0 when x is 3. Now g of negative 2, we're going to move on the x-axis, 1 right here to negative 2 on the x-axis. But where is our graph when x is -2? It's down here at 1, 2, 3, -3. So our y coordinate is -3 when x is -2. Now, is g of x linear? Now that word linear, just like it sounds, it means, is this the graph of a line? And we see that it's not. This is not a graph of a line, therefore it's not linear. Let's move on to the next example. Now for the next example, we're told the polynomial function p of t equals 1.875 times t to the second power minus 30t plus 200. And this function models a typical athlete's heart rate in beats per minute, where t stands for minutes, after the exercise has stopped, where t is between 0 and 8 minutes. Letter A, what is the initial heart rate when the athlete stops exercising? So the initial heart rate, as soon as the athlete stops exercising, we're going to substitute 0 for that point. That's point 0. We're substituting 0 for t into the original function. So everywhere we see t, we're going to substitute 0. And that becomes p of 0, and it's equal to 1.875 times t squared, but remember we're substituting 0 for t. So 0 squared minus 30 times t, minus 30 times 0. Again, we're substituting 0 for t, plus 200 at the end. Now we need to simplify. Now p of 0 equals that 1.875 times 0 squared. 0 times any number is 0. So minus 30 times 0 again is 0, plus 200. So we'll get that initial heart rate as being 200 beats per minute. Part B, what is the heart rate after 8 minutes? Now we're using the same function as before, except for now we're substituting 8 everywhere t is. And we get 1.875 times 8 to the second power minus 30 times 8 plus 200. Remember 8 to the second power, that gives us 64. We'll multiply times 1.875 minus 30 times 8, 240, and then plus 200. We should get 80 beats per minute. So P of 8 is 80 beats per minute, the heart rate after 80 minutes. Notice that our heart rate is going down. Right after the athlete stops exercising, their heart rate is pretty fast at 200 beats per second, but after 8 minutes, it goes down to 80 beats per minute. 200 beats per minute and 80 beats per minute. Letter C, if you look at a portion of the graph from that P of t function, and we're going to look at the section that runs from t equals 0 to t equals 8. Is the graph rising? Is it increasing as we go from 0 to 8, or is it falling? Is the line going down? We just discussed that. We see that our heart rate is going down, right? It's decreasing, therefore we would describe this graph as falling. Letter D, make a table of P of t, and we're going to start with time 3. And we're going to increase by 1. When is the athlete's heart rate between 80 and 110? So here in our table, we make a column for t, a column for the time in minutes, starting with 3. And on the right side, that column would be the P of t. What do we get when we substitute that number into our function? We're starting with 3, using our same function from before. Remember, we had P of t equals 1.875. So here we have 1.875 times t squared And this is just that function from the beginning, 1.875 times t squared minus 30t plus 200. And for each of these rows, row 1, we're going to substitute 3 for t. So we get 3 squared, that's 9 times the 1.875, minus 30 times 3. We got 3 squared, and then 30 times t, or times 3, plus the 200 at the end. Now when we simplify, 1.875 times 3 squared minus 30 times 3 plus 200, we get 126.875. Next, we're going to substitute 4 for t. So we'll get 1.875 times 4 squared minus 30 times 4 plus 200, and we'll get 110. Now we see here that our heart rate at time point 3 minutes after the exercising ends, was 126.875. And then the heart rate went down to 110. The question wants to know, when will the heart rate be between 80 and 110? Once we get 110, we see that range beginning. Now we just want to find when is the heart rate at 80. And that's at time point 8. So you substitute these numbers till you figure out which values are 80 and 110, and we get time point 4 minutes and 8 minutes. So that range of time when the heart rate is between 110 and 80 is between 4 minutes, and we write our inequality statement as such: 4 less than or equal to t less than or equal to 8. So between 4 and 8 minutes. All right, the next example, we have another function, f of x, and it equals negative 0.064x cubed plus 0.56x squared plus 2.9x plus 61. Now this models the ocean's temperature in degrees Fahrenheit in Naples, Florida. In the formula, x equals 1 corresponds to January. So 1 is the month of January, 2 is the month of February, and then we increase. 3 is March, and so on. Letter A, explain why f of 0 makes no sense in this model. Now, when we discuss x values, remember f of x in parentheses, if we're saying x equals 0, that would not make sense because we know those x values correspond to months of the year. The first month being January, and it's 1. There's no such month that begins with the number 0. That's why f of 0 would not make sense. Letter B, what is the average ocean temperature in March? So now we want to know what is the value of that function when x is 3. So we'll use the function that we were given at the beginning in the directions, and everywhere x is, we're substituting 3. So we get f of 3 equals negative 0.064 times 3 to the third power plus 0.56 times 3 squared plus 2.9 times 3 plus 61 on the end. And when we simplify this, we'll get 73.012 degrees. That's the average temperature, or we can approximate that. We can simplify that decimal to about 73 degrees. That's the average temperature of the ocean in March in Naples, Florida. Now, letter C, we want to use this graph to estimate when the maximum ocean temperature occurs. What is this maximum? Look at our graph. We see the highest point on our graph right here is plotted, and that point is between 84, it touches 88 right here above 84. So 88 degrees would be the maximum ocean temperature. Explain why f of 14 makes no sense. Now, just like before, 0 is not a month that's represented by the numbers. We know we only have 12 months in a year. There's no month represented by the number 14. That's why f of 14 makes no sense. Letter E, what is the domain of this model? The domain. So domain, remember from when we initially discussed functions, domain is all of your x coordinates. We have already stated that our x coordinates represent months of the year, starting with 1 being January. How many months of the year are there? There are 12. So our domain would be the numbers 1 through 12. All right, the next problem, we have sales of SUVs increased dramatically between 1991 and 1999. In 1991, the sales were approximately 1 million. And in 1999, the sales were about 3.2 million. The growth in sales for that period was roughly linear. And we were given values we want to find for A and B so that this function f of x equals ax plus b models the data. Now we're told that this representation of the increase in sales is linear. So we could see this function f of x equals ax plus b the same way we would look at a function in slope-intercept form. So f of x equals mx plus b, where our slope, or the number in front of x, could be calculated based on two ordered pairs. We're given two different points in time, 1991 and 1999. We'll take those numbers that are represented in those years and write them as an ordered pair. Since the sales increased between 1991 and 1999, we're starting with 1991, that's 0 point. And remember, in 1991, we had approximately 1 million in car sales. So we use 1 to represent 1 million. That ordered pair is 0, 1. So this will be our x sub 1. This will be our y sub 1. And then the second point, we're told that in 1999, that's 8 years later. After 1991 to 1999, that's 8 years later. So our x coordinate changes from being 0 at the beginning to 8 years later. That's our x sub 2. And in that year, 1999, there were about 3.2 million. So we use 3.2 to represent 3.2 million. That's our y sub 2, our second y coordinate. We're going to use these 2 points, x1, y1, x2, y2, to find the slope. Remember, the slope is calculated by taking the difference in y values, dividing by the difference in x values. So in our numerator, the difference in y values, y2 minus y1, we have 3.2 minus 1, divided by 8 minus 0. And we'll get 2.2 divided by 8. So that slope is 0.275. Once you find your slope, then you can write your function. We substitute 0.275 for m. And we also have the y-intercept, because remember, at every y-intercept, your x coordinate is 0. So 0, 1, that 1 is our y-intercept. So we'll write the function as f of x equals 0.275x plus 1. That helps us with letter B. We're asked to estimate the number of SUVs sold in 1993. So using this function from part A, we want to find an estimation of the number of SUVs sold in 1993. So first, let's figure out how many years after our starting point 1993 is. From 1991 to 1993, we just subtract 1993 minus 1991. How many years later? That's 2 years later. So for x, we're substituting 2 into our function from part A. So So everywhere we see x, we're going to substitute 2. We have f of 2 equals 0.275 times 2 plus 1. And we get approximately 1.55 million SUVs that are sold in 1993. Letter C, why shouldn't you use this model to estimate the number of SUVs sold in 2006? Now, this model that we have, f of x, we wrote that function for 0.275 plus 1, it represents the change in number of SUV sales from 1991 to 1999. That's a specific time frame. 2006 is after 1999. That's why we can't use this model to represent the number of SUVs that are sold in 2006. And we'll stop here. That's the last example from 5.1.